oxidation numbers, and now that you've gotten good at figuring out the oxidation numbers, we can actually use these to balance reactions. And we can, if we trace the change in oxidation number, we can balance some reactions that would have been really difficult for us to do using the old trial and error method. Now, because our oxidation number changes when electrons are gained or lost, it makes sense that if one element is, say, gaining 2 electrons, another one has to be losing 2 electrons. And so if we can track the change in oxidation number and figure out how many electrons are moved and balance for that, we can balance the entire reaction. So we're going to do this in 3 categories. And in this first category, we're going to start with simple redox reactions. It's really the same set of rules for all 3, the remaining 2, the ratios and the splits, just having 2 little what do I do in this case type scenarios. But for this first lesson, I want us to focus on the basic rules for simple redox reactions. So in our note packages, we have this reaction, and this is a simple redox reaction, and it doesn't look all that simple to us when we first look at it. But really, it's actually pretty straightforward. So how do I go about using oxidation numbers to balance a reaction like this? Well, we're going to do this in a series of 6 steps. The first step is to assign all the oxidation numbers. So I'm going to go along and using the rules we've been practicing, I'm going to assign oxidation numbers for every single element in this reaction. Now, I'm going to let you know right now that eventually you're going to find you don't have to do every single one. Very rarely do we find that hydrogen and oxygen in our redox species. Usually it's anything but. And you'll find that sometimes you can save yourself a bit of time by assigning just oxidation numbers to those species you suspect to be redox. But for now, we're going to assign them all. Then I'm going to draw connecting lines from before the reaction across the arrow to after the reaction that indicates which species were oxidized and reduced. In this case, we see selenium in its elemental form going from an oxidation number of 0 up to an oxidation number when it's combined of being +4. We see that its oxidation number has gone up and it's been oxidized. To go from 0 to 4, it has lost 4 electrons. Nitrogen was the other species that changed in oxidation number. It started at +5 and went down to an oxidation number of +2. So this is an example of a species where we saw the oxidation number go down, and that means it was reduced, and to go from 5 down to 2, that means it's gained 3 electrons. So that was our third step, was to calculate the electrons gained and lost. It's really important that we draw these connecting lines and figure out the electrons gained and lost because it's going to be the starting point for everything we do. What we have to do next is go, it doesn't make sense for 4 electrons here to be lost and 3 electrons to be gained. They should have to be equal. So we're going to have to find a way to make them equal, and we're going to use a multiplier. We know that I can make both 4 and 3 into 12. If I multiply this by 3, I get 12 electrons. If I multiply this by 4, I get 12 electrons. Now I'd have 12 electrons gained and 12 electrons lost. But what does that 3 and 4 mean? Well, it means if one selenium was moving 4 electrons, then 3 of them would move a total of 12. If one nitrogen was moving 3 electrons, then 4 nitrogens would be moving a total of 12. I'm going to need 3 seleniums and 4 nitrogens to make sure that I have enough elements to gain and lose 12 electrons. So I've used these multipliers to balance just the redox species. I'm going to put a 3 in front of this selenium to get 3 seleniums here, and a 3 after the arrow to keep it balanced. And yes, I know that changes the oxygens amount, but don't worry about it yet. We're only worried about the redox species right now. To get 4 nitrogens here, I put the big coefficient 4 in front of this species. Even though I know it's changing hydrogen and oxygen, don't worry about that now. Just make sure the nitrogens are balanced. I now put a 4 here to make sure the nitrogens are balanced after the reaction. What do I now do about everybody else? I have enough seleniums to move 12 electrons. I have enough nitrogens to move 12 electrons. What do I do about the rest? Well, you just pick whatever coefficients it's going to take to make it work. At this point, I can balance either the hydrogens or the oxygens, and everything else will just work. Now, it's going to be easier for me this time to balance just the hydrogens because they're in just one space, and I see oxygen spread out all over the place. And we call this inspection. So we're going to balance this remaining species by inspection. And I can see that if there are 4 hydrogens before the reaction occurs, then I'm going to need 4 after. Right now I only have 2. And so if I multiply by 2, I will have 4 afterwards. Now, just as a quick check, 2 oxygens and 4 more is 6. And 3 times 2 is 6 more is 12. And we can see that 4 times 3 is 12. The oxygens just balance. So we now balance this entire reaction by first tracking the gain and loss of electrons. Now, in your books, I've given you this equation. We're going to take nitric acid, HNO3, and we're going to react that with hydrosulfuric acid, H2S. And it's going to react to form elemental sulfur, nitrogen monoxide, and water. I want you guys to try to balance this one on your own first. I've put the steps, the 6 step up in front of you on the screen, and I'm going to go through them one step at a time. So get as far as you can, pause this video here, get as far as you can, and if you get stuck, go ahead and play it forward just a little bit up until you can figure out the next step, and then try and do that again on your own. Let's see if we can't balance this reaction using the 6-step method that I've given you. Pause the video now and see how far you can get. All right, well, the first step was to assign all of our oxidation numbers. And so I've done that for you here. You'll notice that the hydrogens maintain their oxidation number of +1 all the way through the reaction, and the oxygens maintain their oxidation of -2 all the way through the reaction. So the relevant species here are the nitrogens and the sulfurs. When we compare across our reaction arrow, I can see that sulfur went from -2 up to 0. So my oxidation number actually increased in this case, and that means it was oxidized. Nitrogen went from an oxidation number of +5 in my nitric acid down to +2 in my nitrogen monoxide. Its oxidation number decreased in this case. So we're going to draw those connecting lines and figure out the electrons gained and lost. Start by drawing your connecting lines. It helps us to identify which species we're balancing at the beginning. We know that we're concerned only with the sulfurs and the nitrogens. Now, to go from -2 up to 0, we had to have lost electrons, and I can see we've lost 2 of them. To go from +5 down to +2, we have to gain negatives. We gain 3 electrons. So that's our next step. We've indicated the electrons gained and lost. Now you need the multiplier. What can I make these both into? Well, a common factor for both 3 and 2 is to make them into 6. So I'm going to multiply the sulfurs by 3 and the nitrogens by 2. If 1 sulfur moves 2 electrons, 3 sulfurs will move 6 electrons. If 1 nitrogen moves 3 electrons, 2 of them will move 6. I'm using these the 3 and the 2, as the starting point of my balancing. So because I want to have 3 of these sulfurs, I need to put a 3 in front of this species and this species. I know it changes everything else. We're not worried about that yet. In order to get 2 of the nitrogens, I need to put a 2 in front of this whole species and this whole species. Now we're going to balance the remaining species by inspections. And you can choose to balance either the oxygens or the hydrogens. It doesn't matter, but that will be our last step. And you'll see that we need to get a total of 8 hydrogens. 2 plus 6 more is 8. Or we could also be taking a look at, we need a total of 6 oxygens. We already had 2, so we need 4 more. Either way, I had to put the coefficient of 4 to balance this reaction. So I'd like you guys to practice balancing reactions that are simple, just using these basic 6 steps. Now, if you flip to your workbook section, we've said page 1 will come later on. Pages 2 and 3 we've already worked on. Pages 4 and 6 are where you're going to find practice questions on balancing reactions. And you'll see they've been separated into simple ratios and splits. Page 6 is a better place to start because I've already done the beginning steps for you. I've figured out all the oxidation numbers, I've drawn the connecting lines for who went up, who went down, and I've marked change in oxidation number. So you can continue on from there. But on page 4, it's the exact same set of questions, but without any of the starting points done. So it's really up to you how you choose to attack this, but at the very least, do the balancing of simple redox reactions on page 4, and in our next lesson we will show you how to make accommodations for ratios and for splits.